Our Aerospace Engineering 339 final project was interplanetary travel using nuclear propulsion to Triton.
Why Triton? Triton is a moon of Neptune full of scientific opportunity that was only visited once by Voyager 2 in 1989. Thought to be a captured Kuiper Belt object, it sits in a retrograde orbit very close to Neptune. It is by orders of magnitude the largest captured moon in the solar system. Triton's increasing proximity to Neptune means that it is likely to cross the Roche limit and break apart, forming a magnificent ring system around the ice giant. These conditions give Triton some of the most interesting geological and meteorological points of interest in the solar system. Previous readings indicated the presence of a liquid water subsurface ocean heated by extreme tidal forces from Neptune. This is remarkable given how far beyond the Sun's ice line Triton formed and currently resides. The tidal energy also powers cryovolcanoes on the surface, which recover large swaths of the surface regularly. The moon also has been able to hold onto a wispy atmosphere consisting mostly of nitrogen that has been able to form clouds above the surface.
To get to Triton, we will use nuclear propulsion because it is about twice as efficient as chemical propulsion and provides more thrust than electric propulsion.
Now we will discuss two relevant missions, Odyssey and Cassini. The Odyssey mission is NASA's current proposed plan for a spacecraft to visit the Neptune-Triton system. It will be launched in the 2030s with the SLS Block 2. Odyssey will use a chemical propulsion system in space to reach an orbit around Neptune, and from there it will conduct 46 flybys with Triton. And now, the successful Cassini mission was launched in 1997 and ended in 2017, and it was the first man-made object to orbit Saturn and land on an outer solar system body. The propulsion system was also chemical, with both a monopropellant and bipropellant system, with two engines providing each 445 newtons of thrust. Overall, our team took a deep dive into research for this project, as nuclear thermal propulsion has never been used before in space missions.
The mission will begin with the launch of a probe from Cape Canaveral to an orbit of 400 kilometers using the SLS Block 2. Next, it will perform a burn to give it an encounter with Jupiter for the purpose of providing a gravity assist, which is much more effective than a direct Earth to Neptune transfer orbit, as it uses energy from Jupiter rather than thrust. The assist from Jupiter will help the probe achieve an encounter with Neptune, where the probe will need to perform an inclination adjustment burn to match Triton's orbital velocity. Once the probe is in orbit of Triton, it can begin collecting data and transmitting it to Earth for analysis. The system cannot exceed a mass of 118,000 kilograms or the size of the SLS Block 2 payload fairing. It must be able to provide 13.82 kilometers per second of delta V with no more than 89,000 kilograms of fuel. It must be able to withstand the harsh space conditions such as solar rays and radiation, as well as avoid any debris it may encounter on its journey. The size of the system cannot exceed the size of the SLS Block 2 payload fairing or its mass capacity, which are shown on the slide.
Given our design requirements, the team designed a nuclear thermal expander cycle engine. This is similar to a regular expander cycle, except instead of using a traditional combustion chamber, the propellant is heated using a nuclear reactor. To calculate performance characteristics of our engine, we modeled most of the flow as undergoing either isentropic expansion or isentropic work, with the exception of Rayleigh flow for process 4 to 5 and a rough estimation method used for process 2 to 3. This method was used due to the complexity of low-temperature gas and phase change analysis, which was outside of the scope of our report. Using this analysis, we find that to achieve 1,000 seconds of specific impulse, our chamber temperature would be around 3,440 degrees Kelvin, which is slightly lower than the chamber temperature of the Space Shuttle main engines.
All previous spacecraft have flown with nuclear thermal propulsion because of political hesitancies and the cost of radiation hardening. This meant the team's analysis could only compare itself to theoretical values. Team Q has found that nuclear thermal propulsion would be a feasible way to take science quickly to the moon of Neptune, Triton.